Today's focus is on a significant shift in how physiological signals from sleep might be utilised for systematic health monitoring. Traditionally, polysomnography, or PSG, has been a diagnostic tool confined to sleep-specific disorders, things like obstructive sleep apnea or narcolepsy. However, a recent study published in Nature Medicine by Thapa and colleagues introduces SleepFM, a multimodal foundation model that reinterprets sleep as a comprehensive window into future disease risk. By using over 500,000 hours of sleep data, this research demonstrates that the language of sleep can predict 130 different physical and mental health conditions, up to 6 years before clinical onset sometimes. PSG is the gold standard of sleep medicine. It's incredibly high-dimensional, capturing brain activity via EEG, cardiac rhythms via ECG, and respiratory effort, blood oxygen, and muscle tone. Despite this richness, the data is historically underutilized. Most clinical analysis is quite reductive, stripping away the complexity of the waveforms to produce simple metrics like the apnea-hypopnea index or basic sleep staging. Furthermore, scaling AI in this domain has faced three major hurdles. First, data is siloed and inconsistently labelled. Second, PSG configurations vary widely between different clinics. One lab might use 6 EEG channels, another only 2. Third, manual annotation of sleep data is labour-intensive and suffers from high inter-rater variability. This has limited most previous models to small datasets and narrow supervised tasks. SleepFM addresses these challenges by moving away from narrow supervision toward a foundation model architecture. The researchers curated a dataset of 585,000 hours of PSG recordings from approximately 65,000 participants under 4 primary cohorts, including the Stanford Sleep Clinic and BioSerenity. The technical core of SleepFM is a new contrastive learning approach called Leave One Out Contrastive Learning, or LOOCL. In standard contrastive learning, a model learns by comparing 2 versions of the same data. In the multimodal context of sleep, SleepFM learns by aligning representations across 4 distinct modalities: brain activity, heart activity from the ECG, respiratory signals, and electromyography, EMG. For any given 5-minute segment of sleep, the model tries to maximize the similarity between one modality, say the heart rhythm, and the average of the other 3 modalities from that same time window. This forces the model to find the common physiological truth shared across the brain, heart, and lungs. Importantly, the architecture is channel agnostic. It uses a one-dimensional convolutional neural network for initial feature extraction, followed by an attention pooling mechanism. This allows the model to process a PSG recording regardless of whether it has 2 channels or 10, meaning that it's uniquely robust for real-world deployment where equipment standards may vary between different clinical environments. The most compelling aspect of the work is the phenome-wide evaluation. The researchers paired sleep recordings with electronic health record data, mapping diagnostic codes to 1,868 phenocodes or disease categories. The model was tasked with predicting the onset of these diseases over a 6-year horizon, excluding any cases where the disease was already present at the time of the sleep study. SleepFM achieved a C index, that's a measure of how well the model ranks patient risk, of at least 0.75 for 130 conditions. The performance in specific categories is quite noteworthy. It predicted all-cause mortality with a C index of 0.84 and dementia at 0.85. In the cardiovascular space, it achieved 0.81 for myocardial infarction, 0.8 for heart failure, and 0.78 for atrial fibrillation and stroke. So just to help interpretation of what these C index values of around 0.75 to 0.8 mean, the C index is always a number between 0.5 and 1. 0.5 indicates that it's a coin flip than a random guess at predicting disease. 1 means that the model's a perfect fortune teller. It perfectly predicts the order in which every patient will get sick. This almost never happens in real life though. A value in the 0.7 to 0.8 range means that the model's decent and is getting the ranking right for about 70 to 80% of pairwise disease comparisons. So it's a measure of discrimination. It doesn't tell you when someone might get sick, but it tells you how well the model can pick out the high-risk person from a crowd for a specific condition. When compared to a demographics-only baseline which uses age, sex, BMI and race, SleepFM showed substantial improvements in neurological and mental disorders. The area under the ROC curve gains ranged from 5 to 17%. For example, in predicting Parkinson's disease, SleepFM achieved a C-index of 0.89. This suggests that the model is picking up on subtle physiological precursors in the sleep architecture that precede traditional clinical symptoms. Beyond disease prediction, SleepFM was validated on standard sleep analysis tasks. It performed competitively with specialized state-of-the-art models like USleep and YASA for sleep staging, achieving mean F1 scores between 0.7 and 0.78. For classifying the presence of sleep apnea, it reached an accuracy of 0.87. So no single one of these results was sensational, but the combination of results across such a broad range of conditions is quite impressive. The researchers also addressed the generalization gap. It's common for medical AI models to fail when moved to a new hospital. To test this, the team used the Sleep Heart Health Study dataset, a multi-center cohort that was completely excluded from the pre-training phase. SleepFM on this dataset demonstrated strong transfer learning on the unseen data, maintaining high predictive accuracy for cardiovascular outcomes and mortality. Furthermore, the model proved robust against temporal shifts. When tested on a separate cohort of Stanford patients from 2020 onwards, data that didn't exist when the model was being developed initially maintained its performance levels, suggesting the features it's learned are stable over time despite changes in clinical practice. An interesting finding from the ablation studies that they did is how different modalities contribute to different predictions. Brain activity signals were the strongest predictors for mental and neurological conditions, as you might expect. Respiratory signals were more predictive of metabolic and respiratory disorders. ECG, or EKG for the American audience, were, as expected, more informative for circulatory diseases. However, the overall predictive power was highest with all modalities combined. This reinforces the multimodal necessity of the foundation model. The systemic health of a patient is not contained to any single organ system, but in the interaction between them during the restorative phase of sleep. So while these results are impressive, several hurdles remain for clinical integration. First is a referral bias. The training data comes largely from patients already suspected of having sleep disorders. We don't yet know if these predictive patterns held in a completely healthy, asymptomatic general population. Second is a challenge of interpretability. Like many deep learning models, SleepFM is effectively a bit of a black box. While we can see which modality is most important for a prediction, we can't yet pinpoint the specific waveform feature, a particular spindle frequency or a specific heart rate variability pattern that triggers the high risk score for something like dementia, say. For clinicians to act on high risk of stroke in 6 years coming as a warning, they'll require more granular explanations. Third is the hardware gap. PSG is expensive and inaccessible for mass screening. For SleepFM to have a population-level impact, these foundation models will likely need to be adopted for high-quality wearable data. The researchers acknowledge this, noting that as wearable technology advances, models like SleepFM could offer a non-invasive, real-time health monitoring system. So what are the takeaways? SleepFM represents a pivot point in biosignal analysis. It moves the conversation from does this patient have sleep apnea to what does this patient's sleep tell us about their systemic health trajectory across a number of areas. The work shows that foundation models can successfully learn the kind of language of sleep from massive unlabeled and heterogeneous datasets. The ability to predict 130 conditions from a single night of sleep, with performance that exceeds a lot of standard clinical baselines, is a significant achievement. The takeaway for health systems and clinicians is clear. Sleep data is no longer just for sleep doctors. It can be a dense longitudinal biomarker for things like aging, cardiovascular resilience, and neurodegeneration. While further work's needed on population-wide validation and interpretability, SleepFM provides a scalable, label-efficient framework for preventative medicine. The path forward is to see how these sleep representations can be fused with other data streams like genomics, long-term electronic healthcare record trends, to create a truly personalized early warning system. It's one data point within that architecture. It's an optimistic outlook for the field that has until now been looking at sleep with one eye closed.